Here's the solution to homework set number 2 for ECE 321. Now, in this problem, we're looking at building sensor circuits, basically temperature sensors. The thermistor we're using has a nonlinear relationship of resistance versus temperature, like so. What I want to do is come up with a linearizing circuit, make this more linear. One way to do that is this guy. If I choose RA and RB correctly, I can make the resistance close to linear over a range. In this case, I want to make it the range of 0 degrees to 30 degrees Celsius. Now to do that, I could guess again, or let MATLAB guess for me. To do that, I need to create a function in MATLAB. In this case, I'm going to call it thermistor.m. What I'm going to do is I'm going to guess what RA is. I'm going to hard code RB equals 1000. The reason I did that is I was having problems getting it to solve. So I tried 100 ohms, 1000 ohms, 10,000 ohms, trying to get something where I get an answer other than RB equals 0 or RA equals infinity. And 10,000 worked eventually. What the code does is I guess RA, it then calculates what's the resistance of the thermistor at 0, 15, and 30 degrees Celsius. It then calculates the circuit impedance at 0, 15, 30 degrees Celsius, and then takes the difference. If I look at the resistance, I've got something at 0, something at 30, and something at 15. If I do a straight line approximation in the midpoint, that guy right there is the error. How much does the resistance at 15 degrees differ from the average of the two endpoints? And J is the sum squared error. Minimize J, or try to make this linear. If I run fn search with my initial guess at 3000, it says RA should be 1958.8 ohms. And the difference from linear is basically 0. So that's one valid solution. There are others. And I can check that. If I plot the resistance versus temperature, that's what it looks like, highly nonlinear. Find the network's resistance versus temperature. It looks very much like a straight line. That's problem 1. Problem 2, using the answer from problem 1. Design a circuit that goes from minus 10 degrees to plus 10 degrees as temperature goes from 0 to 30. So to start out, build a voltage divider. I chose a 10K resistor. That's somewhat arbitrary. And then find the voltage at 0 degrees, voltage at 30 degrees, add an instrumentation amplifier. As the voltage goes down, the output goes up. This goes to minus 10 to plus 10. So I connect to the minus input. The gain I need, output changes by 20 volts as the input changes by 1 volt. So the gain is 19.01. Pick this to be 19.01 to 1 ratio. And the offset, I want the output to be 0 at midband. The midband voltage is 3.85, so that's your offset voltage. So this circuit will go from minus 10 to plus 10 volts as temperature goes from 0 to 30 degrees Celsius. And checking, if I plot that, sure enough it goes minus 10 to plus 10. It doesn't quite pass through 0 at 15 degrees C. There's a little bit of bend to it. That's because the voltage division is also nonlinear. Calibration, problem 3. Given my voltage versus temperature, I can come up with a function. If I measure voltage, tell me what the temperature is. And here I can do least squares. I know the voltage, I know the temperature. Find A and B to minimize the sum square difference between the two. And you get temperature is 1.47 times voltage plus 15.8. And if you plot the two, the blue line is the actual temperature versus voltage. The red line is linear curve fit. Worst case, it's off by 1.06 degrees, right here. If I do a parabolic curve fit, all I need to do is change the basis. Make the basis voltage squared, voltage in 1. I now have a parabolic curve fit. That's your b squared, v in 1 weightings. Now the error is off by 0.3 volts. Better curve fit. And you could do 4th order, 5th order, 6th order polynomial. Pick your favorite. Problem 5 looks at another way to do this. If I take a 555 timer, the period is a function of R1, R2, and C. If R2 changes with the temperature, then the period changes with the temperature. The frequency is 1 over period. The frequency changes with temperature. So if I build this circuit, take the same resistance I had before, and find the frequency, this is what it looks like. As temperature changes, the frequency changes. So if I can measure frequency, I can tell you the temperature. To come up with that relationship, I can do a curve fit. Well, in Circuit Lab, I can check. I calculate at 15 degrees C. R2 is 1582 ohms. It should be 2.89 millisecond period. Circuit Lab says 2.94. That's the circuit. There's the output voltage, a square wave. This is the capacitor charging, discharging, charging, discharging. Problem 7 is do a curve fit. If I can measure frequency, what's the temperature? If I choose a linear curve fit, my basis is now hertz and 1. Doing least squares, that's the weighting. 0.66 times hertz minus 55 is temperature. And that's the relationship. Here's my frequency. The red line is my straight line curve fit. The blue line is the actual temperature. That's my calibration function. Parabolic curve fit would do better. It'd actually do better if I looked at the period rather than frequency, since period is linear with R. But that's homework set number 2 for ECE 321.